Today, we're very fortunate to have with us Sonia Tikoo at Rutgers University and Ben Weiss of MIT, and they're going to talk to us today about the origin and evolution of the lunar magnetic field. Let me put this in context. Last week, we heard from the NASA Administrator, Jim Bridenstine, on Space Directive number 1, to the moon to stay. And next week, we will, in fact, actually in 2 weeks, next week is Thanksgiving, we will be hearing from Lindy Elkins-Tanton on models for the thermal evolution of the moon. So let me introduce our speakers today. We have Sonia Tikoo, who is a professor, as I mentioned, at Rutgers University. Sonia got her BS with honors in geology and history at the California Institute of Technology and her PhD at Massachusetts Institute of Technology in 2014. She served as a postdoctoral researcher at MIT and also at University of California, Berkeley in the Berkeley Geochronology Center. And Sonia's interests are very much in paleomagnetism, but also in the processes that are involved in that, as well as in things that record paleomagnetic activity. And in addition, trying to understand the implications of that for, in fact, the major processes of planetary evolution, formation of the solar system, and so on. She's done some really interesting recent work in the Chicxulub impact crater and thinking about the ways in which magnetization operates in a very real impact crater, which of course is being sampled through the drilling, etc. We're also very fortunate to have with us Ben Weiss from MIT. Ben's interests are in paleomagnetism and geomagnetism, meteorites, planetary geophysics, and as with Sonia, Ben really works on trying to understand the overall implications, not just, okay, how do we determine the paleomagnetic record, but what does it mean in terms of the evolution of the planets as a whole, the origin of the solar system, and so on. Ben got his BA in physics, magna cum laude from Amherst College in 1995, and a master's and PhD in planetary science and geology at the California Institute of Technology. And Ben has received the McElwain Award of the AGU and is a fellow of AGU, and currently he's a faculty member at the Massachusetts Institute of Technology. So we're really excited about today's event because, in fact, the origin and evolution of the lunar magnetic field is critical in our understanding of what's going on in terms of, again, the origin and evolution of the moon. And we'll see, for example, that these things we've talked about earlier have huge relevance to how we can use the magnetic field to deconvolve the complex signal of lunar evolution. And this will feed definitely into our next class in 2 weeks by Lindy Elkins-Tanton on, again, the evolution of the interior. So without further ado, let me turn things over to Sonia, who will lead the discussion of the origin and evolution of the lunar magnetic field. Sonia?
Hi. Hi, everyone. Thank you for inviting me and Ben to give this talk today. Switch over to my PowerPoint. All right, so today we're going to talk about lunar magnetism and the evolution of the ancient lunar dynamo. So to start off with, core dynamo magnetic fields are generated within terrestrial or rocky planetary bodies by advection of liquid metal within the core. And basically, in order to have advection and a liquid metallic core, you have to have a few things to start off with. One, your planet needs to be differentiated and segregated into a metallic core and a silicate mantle. That means your body has to have a hot origin in order to do that. So once you have a core, in order to sustain advection, you have to have a mechanism that powers it. And that traditionally can be through convective heat transfer, which tells you something about the thermal evolution of your planetary body and the core. Can be powered in part by chemical buoyancy. Once an inner core starts to grow and you freeze out preferentially the liquid metallic, you freeze out the metallic iron, and then the light element rich liquid rises up to the top of the core that's residual. And then finally, you can have exotic dynamo mechanisms that we'll learn a little bit more about later in this talk, which are driven by mechanical stirring of core fluid. And that means that there must be some mechanical perturbation of the core to generate instabilities. So if we take a walk around our solar system, Earth, we're currently sitting in a nice around 50 microtesla magnetic field, getting a little smaller in size. Mars used to have a magnetic field, but doesn't anymore. And we think that it may have died around 4 billion years ago, but that age is not completely certain. Ganymede currently has a magnetic field that's pretty weak, about 700 nanotesla. The planet Mercury has a magnetic field that's about 200 nanotesla. And we've, through paleomagnetism, been able to show that several early planetesimals, such as the asteroid Vesta, used to generate magnetic fields that likely went extinct very early on, within probably the first 100 million years of the solar system, but that's just driven by kind of rapid core cooling in these small bodies early on. Now, what makes the moon a really great target for paleomagnetic studies is that it falls right in the middle of this size range between the terrestrial planets, which still can have magnetic fields today, and the smaller planetesimals where we expect to see short-lived magnetic fields because the bodies are small and cooled off quickly. So in terms of studying the magnetism of the moon, the big questions that we want to answer, or have been answering over the past decade or so or more, is that we know right now that there's no current dynamo magnetic field operating within the moon, but we want to know if it generated a core dynamo in the past. And if so, we want to know how strong it was, what powered it, and how long it persisted. And so today, we're going to walk through a few things. I'm going to start off by talking about the historical development of this field of lunar magnetism. Then I'm going to talk about possible mechanisms that may have produced a core dynamo on the moon. Then I'm going to get into the paleomagnetic methods that people like me and Ben use to study Apollo samples and unravel their magnetic histories, before segueing into our recent results and what we've learned from lunar paleomagnetic studies about the history of the dynamo. During section 4, Ben will take over and continue with some more recent lunar paleomagnets being done at MIT, and then he'll continue on with the implications, Crustal magnetism, and the next steps for what we're going to do in lunar exploration in the future. All right, so let's begin with the historical development. So prior to the kind of Apollo era and the space race, we didn't know much about the moon's magnetic history. The Luna spacecraft flew by and realized that there is no current dynamo field. But one thing that was interesting is whenever the Apollo missions went to the moon, they took surface magnetometers to the landing sites and plunked them down, and they made magnetic field measurements of what was on the crust wherever they landed. And the strength of the magnetic field that was around varied depending on landing site. You can get as low as 3 nanotesla at Apollo 15 up to 300 nanotesla, which I think was maybe 16 or 14, somewhere without a lot of impact melt rocks. And then one thing that was immediately obvious is that these are small field values, but they're not null, like the background magnetic field that you'd expect if there was no crustal magnetism just in the solar system would be around 2 nanotesla or something of that nature, but they're stronger values. So that tells you that at some point in the moon's history, there was magnetism there that imprinted magnetization into the rocks on the lunar crust. But one thing to take away, though, is that these strengths are way weaker than the terrestrial field that we're sitting in right now. So it implies that the moon might have had a historic magnetic past, but it's clearly not there today. So since we couldn't learn much immediately from just these Apollo surface measurements, we really rely on looking at samples that were collected during the Apollo missions and doing paleomagnetic studies. And this was facilitated by the really awesome hard work of the astronauts who brought back several hundred kilograms of material from the moon. So an earlier generation of paleomagnetists could actually measure a bunch of lunar rocks and try to get sort of a first pass understanding of the moon's magnetic history. So what we're looking at here is, I'm just going to move my mouse around. On the x-axis, we're looking at time before present, age, basically, of each sample. Each sample that was studied during the Apollo era is a different black dot. And then on the y-axis here, we're getting the paleo intensity that was inferred from each sample. So what I mean by paleo intensity is operating under the assumption that each rock acquired its magnetization during primary cooling when it formed, on the moon, the paleo intensity is the strength of the magnetic field that was required to be around at the time the rock formed to produce the magnetization that we observed. So what we found, and here's Earth's magnetic field at 50 microtesla for reference. And what we found is that early on in lunar history, from about 4 billion years ago to about 3.6 billion years ago, there seems to be this time of higher paleo intensity values, but also a lot of scatter, like an order of magnitude scatter, which is a little bit interesting. And then there seems to be this drop off maybe, and then there are all these values that persist up to basically yesterday that are non-zero, and that's interesting too. We know that there's no dynamo field today, so this was all kind of mysterious. And so at the end of the Apollo era, we had a lot of questions that were remaining. One, due to a lack of samples that were really, really old, we couldn't really assess the understanding of whether there could have been a dynamo at the beginning, earliest stages of the moon. But then later on, after 4 billion years ago, we have paleo intensities that are pretty high. But according to models of lunar thermal evolution, I'm sure Lindy will tell you more about this in 2 weeks, we don't expect to have purely thermal core convection after around, early models would say around 4 billion years ago. Alex Evans did some great work recently in 2014 that said that if you add water to the lunar mantle, you could extend the lifetime of a convective dynamo to about 3.5 billion years ago. But the point is that there are data points that are non-zero after the time when we think this is purely core convection, thermal core convection should have ceased. And another issue is that if you use the same kind of dynamo scaling laws that we use to understand, other planetary dynamos and stellar dynamos, the moon should not have been able to generate a magnetic field stronger than, I'm being extremely generous when we say 20 microtesla. Most models say just a few. And here we have all these early high field values that are much higher than what is thought to be theoretically possible for a convective dynamo. So there were a lot of things we didn't understand at the Apollo era. And one thing I will also mention is some of the paleo intensity techniques that they were using were kind of quick, and we study the samples in a lot more detail now in terms of unraveling their magnetization and also assigning ages properly to the samples using geochronology to make sure the age of the magnetization in each rock is actually the same as the geochronologic age that's assigned to the rock. So in view of all these uncertainties, what we have unresolved at the end of the Apollo era is, were there actually substantial, 10 to 100 microtesla fields on the ancient moon, or could some of those data points be contamination from sitting in the Earth's magnetic field for a long time, or contamination from sample handling and exposure to strong magnetic fields? We had to rule those out, or impact magnetic fields that are generated from plasmas on the moon. You have to filter through all those possibilities. Then if we can show after all of this that there was a dynamo record, or show that there was magnetization in these rocks, we have to say, all right, is that actually from a core dynamo, or could it have been some transient magnetic field from an impact? So we have to narrow down that possibility. And then finally, if there was a dynamo operating within the moon, how was it actually generated? What was the power mechanism? And when did it finally decline and turn off? And so those are the motivating questions that have pushed us in the last 10 years. So before I talk about the paleomagnetism, we'll get into some of the possible ways that the moon could have generated a core dynamo. So we think due to a variety of geophysical techniques that the moon has a core from moment of inertia and laser ranging and seismic. So here is basically a seismic velocity profile that was written in 2011 by Renee Weber that shows that the moon probably has a core that is, somewhere around 300 to, up to 400 kilometers in radius, depending on which interpretation you look at. And we think it has a fluid outer core and a solid inner core. And so, yeah, the fundamental building block for the moon to generate a dynamo is there. We have a metallic core. But the question is, what can that core actually do to generate a magnetic field? So there are 4 possibilities that we've been considering. 2 of them are sort of our conventional understanding of how most planetary dynamos work, at least for terrestrial planets, and these are convective dynamos. One is just thermal convection, just core cooling, fueling, rising, and falling of hot metal within the liquid core. And then once you have the inner core start to crystallize, then the added contribution of latent heat release during core freezing and also the buoyancy of the rising lighter element enriched liquid that's left over in the liquid outer core, that can power thermochemical convection. So this is our understanding of like how the Earth's dynamo works. It's powered by thermochemical convection today. But then for the moon, we're also thinking about a couple alternative dynamo mechanisms that have been preserved, and these are mechanical in nature. So the first idea is that basin-forming impact early in lunar history, perhaps before around 3.8 or so billion years ago, these large impact events basically like shake up the mantle and kind of cause the moon to like wobble or librate. And then that libration triggers core instabilities, and that unstable fluid motion can generate transient dynamos. Each dynamo, mini dynamo, I can say lasts a few thousand years at most, according to the model. And then there's another mechanism, mantle precession, that can generate a longer-lived dynamo. So the idea behind this is in the past, the moon was closer to the Earth than it is today, and so the Earth's gravity can pull on the moon's like mantle and tidal walls and kind of cause the precession axis of the mantle to become decoupled from that of the core. And again, you have this differential rotation of the core and the mantle, and that can drive instabilities in the core by stirring the core. So these are the four mechanisms, and each one has sort of a predicted power that it can contribute to a dynamo, predicted field intensity that it can produce. So what we're looking at in this plot is these are different lunar thermal evolution models that assume different dynamo mechanisms and initial conditions. So on the x-axis, we're looking at time before present, and on the y-axis, we're looking at the core mantle boundary heat flux that is calculated for each model. Now, in order to sustain thermal core convection, you have to have a heat flux coming out of the core that is higher than the adiabatic threshold. So the adiabatic threshold calculated for the moon is somewhere between 2 and 10 milliwatts per meter squared, and that's the gray box that we have here. And then each model, assuming different initial conditions like initial temperature differential at the core mantle boundary and whether there's water in the mantle or not, produces a different outcome. So for purely thermal convection, these were the cooler colored lines. What we see is that purely thermal convection tends to cease by around 3.5 billion years ago. Thermochemical convection, whenever you can add in latent heat, it can persist for longer, perhaps even past 2.5 billion years ago. And if you have like a thermal blanket around the core at the beginning of its evolution, you can delay the onset of the dynamo and then have it last longer afterward. But the amount of power that's generated by all these convective mechanisms seems to be fairly puny compared to what a procession dynamo, in theory, might be able to do. And so here are all the curves to the convective dynamos, and then the procession dynamo, and these are from Dwyer et al. 2011 in Nature. And basically, the reason there's 3 lines here is we don't know exactly how fast the moon migrated away from the Earth at that point in time. So the faster, if the moon migrated really fast, then the dynamo would shut off earlier, and if it migrated slower, it would shut off later. But here in the green is sort of the nominal model. But you see the procession dynamo not only lasts longer in theory, but it also generates a lot more power. So on top of this, each dynamo mechanism doesn't just have a predicted intensity and power, it has a predicted lifetime. So in summary, we can say that thermal convection dynamos, I mean, we can push this line around to wherever, but in general, they last until at most about 3.5 billion years ago. Impact-driven dynamos, those transient dynamos, can only last as long as there were basin-forming impacts, so about 3.8 billion years ago. 3.7, something like that. Mantle precession, we don't really know how long that mechanism could power a dynamo, so let's just say 2 GA, because that's the nominal model that was presented in that paper. And then thermochemical convection, it could go up until very recently, and it can also operate in either a continuous or a start-stop regime. So this is kind of the framework of what we're thinking about in terms of the dynamo mechanisms and how much power they can produce and how long they last. All right, so now what we're going to do is we're going to shift from this theoretical treatment and actually talk about the paleomagnetism methods that we use to analyze the lunar magnetic history. So whenever rocks form, if there is a magnetic field at the time that they undergo primary cooling, sorry, I had a phone call coming in, so it was a little bit awkward. Okay, so if a rock forms at the time that there's a field around and it's cooling down, the magnetic grains within the rock, these little iron nickel grains, they're all going to become, not all, but they're going to become magnetized in the direction of whatever ambient field is present at the time that they form. So a rock along its entire length scale will acquire a stable unidirectional magnetization. And so that magnetization acquired during primary cooling is called thermal remnant magnetization. Then, if there's no magnetic field around to bias the magnetization direction during cooling, your net magnetization is going to be zero. So each little mineral grain is going to be magnetized in a different way, and you will have a net zero field. So everything will be randomly oriented. So if there was a dynamo record in a rock, we'd expect a rock to be unidirectionally magnetized. So another thing we do whenever we study rocks is we want to demagnetize them from their initial state so we can identify what the original magnetization in the rock was and make sure that we've ruled out contamination from some later magnetic event after the rock formed. So what we do here, and this is a two-dimensional projection, but we study the magnetization vector that's present in the sample. And so the natural remnant magnetization is basically the resultant vector of all the individual vector components inside your rock. So a rock has a lot of different individual magnetic grains in it. Some of them are really hard to remagnetize, and those are the big red grains here on this plot. And other other grains are more susceptible to being remagnetized by contamination, and those are the blue grains in this rock. The NRM is the resultant vector that shows the sum of this entire original magnetization plus any overprints that are there. So what we do in this lab is we slowly demagnetize rocks either by heating them up to the Curie temperature or using alternating magnetic fields to randomize magnetization. We chip away at the magnetism in the rock progressively. So here we apply alternating magnetic fields of 2, 5, and 10 millitesla until we've removed or randomized any overprints that are present. And then we keep demagnetizing the rock until we unravel an origin trending vector. And that origin trending vector should be the original thermal remnant magnetization in the sample if it had one. So that's another thing that we're looking for. And then on top of showing that a rock is stably magnetized, we also want to figure out how strong was the magnetic field that originally magnetized the rock. So if a field is very, very strong at the time a rock is forming in the presence of a field, that field is going to bias the magnetic directions of all the individual grains in the same way. And whenever the rock cools down, that direction is going to get preserved semi-permanently as a magnetization, which is uniform across the entire rock. If a field is somewhat weaker, this process becomes less efficient. So some grains are magnetized the right way and other ones are randomized. But in general, the net vector is in the direction of the ambient field, but the net magnetization is weaker. And again, if there's no field around whenever a rock forms, then there's nothing to bias it, and your net magnetization is zero. So the way this works is that whatever magnetization is recorded is oriented in the same direction as whatever field is present when the rock forms, and the strength of the magnetization is directly proportional to the strength of the ambient magnetic field. So using this toolkit, let's see how we actually analyze a few lunar rocks. So we're going to walk through some recent lunar paleomagnetic discoveries. So one case study that I'm going to feature is a paper that we wrote in 2017 And this was a study of an Apollo 15 regolith breccia called 15498. Now, this sample was pretty cool. So it consists of, it's a regolith breccia. It has Mare basalt clasts, but they're sort of welded together with impact melt glass. And this rock was interesting because it was pretty young. It comes from after this sort of Apollo era inferred high field period in lunar history. Our thermochronometry results suggest that it's between 1 and 2.5 billion years old, but probably closer to the 1 end of that range. And the reason this is a good sample to study is that its cooling time scales from thermal models of like how a melt containing these rocks would cool is at least an hour or so. And the reason we want it to be kind of longer than just a second is we want to be able to rule out transient impact-generated magnetic fields. Impact fields during the basin-forming era could last for up to a day, but after that, like at the time that this rock formed, we don't think they last more than like a second or a few seconds at most. So if a rock took a long time to cool down, it cannot have recorded an impact-generated field. So if it has anything, it has to be from a dynamo. And this was also a good sample to study because the impact melt glass matrix of this rock does not show any shock features. There are no microfractures in the impact melt glass itself. There are clasps within it that are shocked, but we're not really sampling those. And so the lack of microfractures in the glass tell us that this rock is unshocked, and the reason we like that is because shocks can also reset magnetization in rocks, not just heat and thermal processes. So we can rule that out for this sample. And so what we did was we collected 12 glassy samples from the interior of the breccia. So they're from these general zones where I got chips. We had some basalt that was adjacent to the class to help us orient the pieces with respect to each other. It gave us a visual aid. But generally, we took chips from around here, and from the periphery of this class here, here, and here. We got 12 pieces, and we studied their magnetization directions. So now what we're looking at is a vector endpoint diagram of the magnetization vectors in one subsample. So the solid dots on this plot are the magnetization vectors projected into the north and east plane. And then the open symbols are the magnetization vectors projected into the up and east plane. So you can see three-dimensional information in a two-dimensional space. So you can choose to only look at one of these data sets. So let's just look at the open dots for now. You can see that there was some overprint vector that we were able to remove, another overprint vector that we were able to remove, and then we have this green one here that goes to the origin. That's the original magnetization recorded by the rock. So this is just one sample, and we measured 12, right? And so it turned out that all 12 samples had a very robust origin trending, high coercivity, and high temperature magnetization component, which was indicative of something that was acquired during original cooling on the moon. When we looked at the magnetization direction across all the subsamples, they were basically the same. They all fell into the northeast quadrant in the upper hemisphere. So this means that the rock is unidirectionally magnetized too. So this is even more evidence that this is a dynamo record in this sample. We did what's called a Tele-Atelier paleo intensity experiment. So what we do is we stepwise thermally demagnetize each sample, and after each step of demagnetization, we remagnetize the sample in a known field. And so at each temperature step, we look at how much magnetization is remaining versus how much laboratory magnetization was gained at the same temperature. And so each point, basically is like, here's the rock after we demagnetized it to 560 C, and here's how much magnetization was gained after we remagnetized it at 560 C. And the slope of this line for this high temperature component tells us the paleo intensity of how strong the field was at the time that the rock formed. So the ancient magnetization over the modern lab magnetization is equal to the ancient field over the modern lab field. So we gave it a lab field of 5 microtesla and basically multiply that by the slope and get the ancient field value of 5. So what we learned is this sample was recording a dynamo field that was 5 microtesla somewhere, between 2.5 and 1 billion years ago, showing that the lunar field was very long-lived, and it was actually lasted a billion years longer than the previous studies that had come out in like 2013 had shown. Previously, it was thought it lasted till at least 3.5 billion years ago, and we tacked on another billion to that. And so I'm going to switch over to Ben now, who's studying even younger lunar rocks to try to figure out when the field died. So I guess I'll let you take it from there, Ben.
Okay, yeah, so we've been measuring many rocks, and we decided, Sonia and I, just to show you basically examples of the 2 broad types of behaviors that we've observed. Basically, up until the samples I'm about to show you, we observed more or less one form of behavior, which is rocks that are magnetized. And without going into all the details, we've seen many samples like what Sonia talked about, which have convinced us that there indeed was an ancient dynamo magnetic field. And we'll show you a summary of all those data points in a second. But as of very recently, we started seeing another type of sample behavior, and it's represented by these 2 very similar samples to what you just observed. These are also Apollo 15 regolith breccias. On the left, we have 15465, and on the right, we have 15015. And what's distinctive about these samples is they're just a little bit younger than Sonia's sample that she just showed you a few minutes ago. So it's been very hard to figure out how to date regolith breccias. We've recently made some advances on that, and we think these things are about 0.4 billion years on the left and 0.9 billion years on the right. So these are very young by the standards of Apollo samples. And again, they're relatively slow cooled relative to any kind of putative impact generated from magnetic fields. So these things should record a dynamo magnetic field if there was one present. And like before, we went after the very nice matrix melt glass, which is very fine magnetic grains and should be an excellent magnetic recorder. Okay, next slide. This is work led by MIT grad student Miguel Said Migani, and Huapei Wang was a postdoc here. So here we see very different from what we've seen in the past. So after we demagnetized the sample to just 150 degrees C, we removed this huge overprint. And then basically the magnetization vector is scattered and random. It just bounces around randomly and doesn't show any decay in intensity. And if we do a paleo intensity estimate of that, like what Sonia showed you before, so remember the way this works is the magnetization intensity of the rock is proportional to the ancient magnetic fields. And so what we do is we remagnetize the sample in a known laboratory field, and then we measure the magnetization produced by that. We take the ratio of that laboratory magnetization to the ancient magnetization, then that's equal to the ratio of the laboratory field to the ancient field. It presents as a slope in this plot of NRM versus on the vertical axis, that's the magnetization loss that was natural, versus laboratory magnetization gain, which is this what we call PTRM gain. So what you see here is basically all those red points after we remove this big overprint is essentially that has a slope of 0. And in fact, to be precise, it's 0.24 plus or minus 0.24, which basically makes it essentially the weakest paleo intensity we've ever observed for any sample from any body, essentially. I mean, there's nothing like this on the Earth, because the Earth has a dynamo. But here we have a rock that has essentially no magnetization and essentially formed in space-like conditions. Okay, so the next slide. And so here's now a summary. We saw that again for the other sample. So here's a summary of all of our modern data points. So Sonia before showed you the Apollo era data, and there were many points, but we have reasons to think that some of those points have problems, and so we've been, they to first order were important in sketching the fact that there was a dynamo, but the precise intensity variations are probably open to question for a number of different reasons. So these are the points that we're showing you here we think are robust measurements made from modern laboratory techniques. Again, plotted as a function of time. Each point here is a different Apollo sample. Sonia, I, and also a group in France, as well as a group at Scripps have put together. And basically, there are a bunch of blue points and a bunch of red ones. The red ones mean we detected no evidence of any field, and so they're just upper limits. Blue points are actual measurements of dynamo fields. And so what you see here is there are a bunch of strong points around before 3.5, so that the idea that there's a high field epoch that was far stronger than we can imagine from basic theory for a convective dynamo could be produced, shown by this horizontal dashed line. So we validated this Apollo era observation that the field was insanely strong on the early moon. You know, basically Earth's strength, even though the moon's core is maybe there's only 1/7 of the planet's, of the moon's radius, whereas the Earth's core is half. And yet then after that, the field drops off a cliff around 3.5 billion. But then there's Sonia's point here on the right around between 1 and 2.5, which very strongly indicates that there was a dynamo lasting until at least that time. And we're trying to fill in some more points during that period and we do already have some evidence that there are other points in that era that reproduce that. And then finally, these two red points around 0.9 and 0.4 are the ones that I just showed you. We see basically the field is very, very weak. We see no evidence of any field. So if you click the button, Sonia, advance, you'll see that this new line appeared here. So what this horizontal line at 0.1 is, basically if you take all these different dynamo mechanisms shown at the top, so remember these are all the different convective and mechanical dynamos that have been proposed for the moon, and their position in this plot shows the lifetime of the power sources associated with each of these dynamo mechanisms. And you say, given these different mechanisms, how long, what fraction of lunar history do they produce field values that are bigger than 0.1? And the answer is about 90%. So in other words, for almost all of lunar history, more than 90% of lunar history, these dynamo mechanisms collectively predict field values greater than 0.1 microtesla. So what we infer from these 2 points, which are below that, is that they actually indicate that the dynamo had ceased by that time. So we think we have evidence now of when the dynamo finally turned off, and it looks like it's probably around 1 billion years ago. And then it remained off even at 0.4. All right, so that's very new stuff. Okay, next slide. So here's what we're showing here. We think the dynamo, I'll go back one split. Yeah, we have a dynamo epoch before about 1 billion, and then the dynamo turns off after that. And the important thing is, really the only power source that likely could power the dynamo that long is in the late era is core crystallization. So we think that this protracted dynamo until about 1 billion years ago, and then its decline can indicate that the late lunar dynamo was powered in a very Earth-like way, that is by crystallization of the inner core. And probably the earlier dynamo, when the field was stronger, may have required some kind of exotic mechanism with really high power, like procession. And remember those curves Sonia showed you, which predict that procession can produce enormous amounts of power. So there may be 2 different dynamo mechanisms kind of handing off around 3 billion years ago, or before that, procession, after that, core crystallization. Okay, next slide. All right, so next slide. We'll talk about implications. So that's what I just said here. Actually, Sonia's pointed out there's actually maybe even a period before procession when thermal convection likely also contributed to the dynamo. Because at some point the moon's core was convecting without the need for core crystallization. So it's even possible that there was an earlier epoch of thermal convection. Okay, so next slide. So, and we wanted to say a little bit about the crustal magnetic field. So in case you're still skeptical and you think, well, maybe all these samples got remagnetized by, someone sticking a magnet on them, or sitting in the Earth's field for 40 years, and we do worry about all that stuff. In fact, the thing that we're most worried about recently, we've discovered, is that saw cutting at Johnson Space Center clearly remagnetized a bunch of these things, because they did it without any water or coolant, and so they got very hot. And we see that all the time now with rock surfaces that were just cut that have strong magnetization. But anyway, the lunar crustal magnetic field is observed from orbit, clearly demonstrates that there is remnant magnetization and that this cannot be an Earth contaminant. It's a very important and unsolved question. Even though these fields look very weak, you see there are tens of nanotesla in the strongest. It turns out that it's actually very hard to explain even these very weak anomalies, even if you assume that the ancient magnetic field that produced them was Earth strength. And it's just simply because lunar rocks themselves have very little magnetic material in them. And so these actually, the presence of even weak anomalies like you see here, in my mind, provide very strong evidence that there were substantial magnetic fields in the moon in its past. Okay, next slide. So I just wanted to say, point out a point here. So here's the Apollo era record. And there are some a strange kind of inconsistency or possible inconsistency between the Apollo paleointensity record. That should be, it looks like the left side of this got cut off, but this is actually paleointensity values between 1 and 100 microtesla. But what you see here is that, as I already said, the dynamo lasted maybe about 1 billion years ago, but if you look at the ages of surfaces on the moon that are magnetized, as indicated by crustal anomalies measured by spacecraft, you find that only after surfaces of older than 3.9 billion, shown by this horizontal red line, show strong magnetization. And so if you were just to use the observed magnetic anomalies from orbit, you would conclude that the lunar dynamo was very short-lived. And of course, the intensity is poorly constrained, what the ancient magnetic field intensity was from these crustal anomalies, because you can't remagnetize the moon in a known laboratory. You can't bring the moon to your lab and remagnetize it. So all we can do is measure its natural field and not remagnetize it in a known field. So the intensity is very uncertain. But the main point I want to point out here is just that the lifetime of the dynamo inferred from crustal anomalies is much shorter than what we see from the Apollo record. And it kind of underscores why samples are so powerful and so important. And to underscore that more, let's look at the moon, at Mars. Next slide. So this is highly relevant because for Mars, we're about to have another rover that goes there in 2020, and it's going to initiate the Mars sample turn campaign. And for Mars, we have, again, crustal magnetic anomalies, which suggest that the dynamo was around before the early Hesperian, maybe. And then after that, there are no magnetized rocks, shown by this horizontal red line. So that's it. And then so it's been suggested that the Martian dynamo died around that time. That's very important because if it's true, it's coincident with the period of global climate change on Mars, and it's actually been proposed that the death of the dynamo was causal in climate change on Mars. But I just want to point out, the Martian meteorite record, we have one sample, ALH84001, at 4 billion, which is consistent with there being a dynamo at that time. But everything else after that, the samples are very young and basically only produce upper limits. And I just want to say, we don't really know when the Martian dynamo died, and it'll be an important contribution that sample return from Mars will make, is to get the same kind of plot that we have for the moon for Mars, and really see, is it true that the dynamo died around the time of climate change, or was it much more protracted in the way that it was for the moon? So this is just another example of how the moon is kind of a touchstone or a cornerstone for understanding all of the planets. The detail of information we have about the moon is something that we can use over and over again to understand data from other bodies. Okay, next slide. All right, and then we just thought we'd end by talking about next steps. And there's plenty of sample measurements we'd like to make, but I thought it might be fun to talk about exploration or in situ measurements, because I think one of the most important things that's going to be happening in the next few years is the enormous numbers of opportunities for making robotic and human measurements on the lunar surface that are going to allow us to address questions that we can't with the Apollo samples. And the most important question we can't address with the Apollo samples right now very easily is, what was the direction of the ancient magnetic field of the moon? All these samples we brought back are basically regolith samples. They're float samples, maybe with one exception. And so we've only been able to measure the length of the magnetization vector and not its direction. But if we could measure its direction, we could do all kinds of great things. We could start looking for whether the moon's field reversed. We could test whether the moon wobbled in time. We could study tectonics on the moon. There are lots of things. We could understand the mechanism of how the lunar dynamo was generated, which makes different predictions for the direction. So I just wanted to point out that, in situ measurements in the moon are a potentially game-changing contribution to understanding the paleo-directional question. And as an example, take a look at the Apollo 15 site. So here we are. This is on the edge of Hadley Rill. And the astronauts at Station 9A basically drove up to this terrace on the left there. so right on the edge. And they looked out across Hadley Rill and they saw the following. Next slide. So here's the zooming in. Again, forward. That's where they're going to take a picture now, shown by this green. And that's what they saw. Oh, yeah, exactly. Next slide. Basically, that's the other side of the rill. And you see tens of meters of exposure. So click again. And again. So what you see is just huge cliffs of what is clearly bedrock and essentially zero dipping Mare basalt. And so imagine if you could actually get a sample of that, not so easy, but maybe you could make an in situ measurement with some kind of spacecraft. And that rock is clearly in its original position, which would potentially allow you to measure the direction of the lunar magnetic field. Okay, next slide. How could you do that? There's a bunch of different ideas that people have proposed. They involve some kind of you need a fairly mobile platform that can operate in difficult terrain. This is a sketch from former MIT graduate student working with Jeff Hoffman. Basically, they've been advocating for moving around the surface of the moon by hoppers. And that by hopping, we mean basically you can land and then basically jump several kilometers and then land again, and potentially even hover along cliff faces like we just described. So imagine putting a magnetometer on one of these platforms and measuring the magnetic field as you traverse horizontal layers. Not only could you get the direction of the ancient magnetic field, but you could watch the field change in time as you progress through the stratigraphy. Okay, next slide. So coolly enough, there may be just such an opportunity. There will almost certainly be such an opportunity. Maybe I'm overstating it slightly, but we are scheduled to launch the Space IL former Google Lunar X Prize mission led by a group in Israel. Originally, they're talking about December, but it would be very surprising if it didn't happen this year. It's got a hopping platform, and guess what? It's got a magnetometer on it. So we'll see how that goes. So that's coming up soon. Keep an eye out for that. Okay, next slide. And then since I saw you had a talk from Laura Kerber a few weeks ago, couldn't help but pitching something Jim Head and I have been speculating about. Imagine a moon diver-like platform where you basically roll down into a lava tube and measure the magnetic field as a function of a stratigraphic layer, with all these beautifully in place Mare basalts. It would be the ultimate paleomagnetic experiment from a robot that I can think of. So I think even if it's not moon diver, there's going to be some future opportunities like this that would be invaluable. Okay, next slide. So just to end then, so we think finally we have strong evidence that the moon generated a dynamo that lasted from at least 4.2 billion, the oldest sample we have, to at least 2.5 billion, probably to 1 billion, the youngest sample for which we found evidence for a dynamo. All the samples that we've seen after that are essentially completely non-magnetic, unlike anything we've ever seen from another body, totally zero. And, well, I mean, we're not starting to see that on asteroids too, but I mean, certainly the weakest values that we've seen. And then these early dynamo values are super strong. It's hard to understand from a conventional Earth-like dynamo powered by convection that you could produce Earth-strength fields. And so that may have required some unusual mechanical sources like Procession. But then the late dynamo we suspect was powered by inner core crystallization analogous to the Earth. And maybe the next phase of exploration, aside from bringing samples back and measuring more Apollo samples, is making in situ robotic measurements from platforms that have mobility and it can allow us to access this bedrock. And hopefully we can do that on other bodies as well. So thanks very much.
Thank you very much, Sonia and Ben. This is really an excellent presentation, very informative. So our tradition here is that we'll ask a few questions, if you don't mind, and you can sort it out who wants to answer it, or you can both answer it. So let me turn you over to Ariel Deutsch, who will be asking the questions. Ariel?
Okay, so first we have a couple of general questions from the group here. The first is, could you describe some processes that might reset orientation of grains that could affect your studies?
You want to take that one?
Yeah, so I guess there's two ways to interpret the question. One is that if you're talking about individual magnetic grains within a rock, the grains don't actually rotate. It's just the magnetization direction that the grains record that move around. And those can be reset by reheating the rock. They can be reset by shocking a rock by an impact, or if you expose a rock to a strong magnetic field, you know, sometime later, that field strength may be strong enough to overcome the barriers that lock the original magnetization in the rock. So you can reset magnetization in those ways. But if you're talking about moving actual entire rocks around on the lunar surface, then really the only process that's active on the moon these days is impact. So I guess I've tried to answer both interpretations of that question.
Thank you. Our second question is, so you showed some plots that showed data points suggesting that there was a dynamo on the moon early on, and then there was a single data point suggesting that there might have been a dynamo lasting into the more recent history. And the question is, do you think that in the time in between it's necessarily characterized by continuous dynamo, or that there could have been some sort of mechanism shutting it on and off?
It's entirely possible that the dynamo was operating in a start-stop regime. If you look at a paper by Aaron Scheinberg that came out in 2015, he did a model that described a core crystallization powered dynamo, and one of the outcomes in those models was a start-stop dynamo. So it's completely possible that it was not continuous. I mean, one thing I'll add though is that our sample coverage for a good span of lunar history, and I think you saw that in the plot, from about like 3.1 billion years ago up to, you know, more recent times when you have these young ages for regolith breccias. We don't always have good coverage in terms of sample ages from what we brought back. So, you know, part of it is like, where did we land on the moon and where did we get these rocks? There might be other places on the moon that have rocks with different ages, or maybe we need to redate some of these samples and we'll find out that things in the middle got filled in. But it's kind of going to take more work to deconvolve that.
So just a quick interjection here too. I was in looking at the plot of magnetization as a function of time. It's pretty clear that the early magnetization also corresponds to the period of time in which the large basins were forming. And I was just wondering if you could bring us up to date on the latest thinking about the role of impact basin generated transient magnetic fields, and, you know, does the transient field scale with basin size? And, you know, somebody looking at that might say, whoa, there's a great correlation. It's all done by transient fields, and then we don't have those anymore because we have small basins, so the field never was that high. Yeah.
So that's why the paper that you're a co-author on is so important, I think, and you actually helped us come to this conclusion, is that the dynamo record confidently extends to 3.56 billion years, which is only, okay, a few hundred million years after the basin forming era, but confidently still past it. So one of the important things that we've done differently from the Apollo era data is Apollo era data showed, yeah, there's this nice correlation with the basin forming, which you could see in the early data, but exactly how long it lasted, what they didn't know. But now we've confidently extended it to at least 3.56, and I believe Sonia has got some data which shows that it's even past that, or maybe a little bit weaker. So very much after Oriental. So at least in terms of the timing, it's no longer coincident. And then the other point I want to make is that at least the theoretical understanding of how these dynamos work only suggests that they would persist. That is an impact-generated dynamo from basically knocking the mantle and stirring up the core by basically knocking the mantle. That those last for only a few thousand years. So you would expect lots of zero field paleointensities during that dynamo epoch, during that high field epoch, if they were basically impact dynamos. I mean, so far we don't see that.
Yeah, I mean, the probability of any individual rock forming within like 5,000 years of each basin impact is rather low. So, I mean, it would be surprising for us to even have as many samples as we do that are strongly magnetic.
But this underscores again why samples are so important for planetary science, and that the fact that we can get precise radiometric dates is really crucial for establishing that the impacts probably did not cause this.
So just another question about the origin of the essentially core dynamo generation. So another big event that occurred about that time is, in the impact, sort of the big basin era, so to speak, and is of course the aftermath of the lunar magma ocean solidification and essentially an instability that essentially caused negative buoyancy and foundering of a lot of the materials that essentially became the core. So is that whole process or some part of that process maybe linked to inducing convection? For example, is something different than what you talked about. So basically, you have a large-scale, late LMO loss of material that could induce convection. Could that have an effect?
Yeah, there was a paper recently about powering the lunar dynamo from magma ocean, and
right.
Suggested for the early Earth as well. So yeah, we didn't talk about that. We probably should add that to our presentation. That just came out. But you're absolutely
about
right.
it, but it's just the actual conductivity that you would expect in a basal magma ocean is so poorly constrained at this point that it's unclear how feasible it actually is. But in terms of like cumulate sinking and then stirring the mantle and then, causing some thermal disruption at the core mantle boundary, yeah, I mean, those are all conditions that could be plugged into a lunar thermal evolution model. And that's where people like Alex Evans can do the work and we'll tell him what answer he should get.
The other thing is our dynamo record right now only goes to 4.2. So I think that probably happened earlier. Correct me if I'm wrong. We would love. Yeah, we would love to get samples of maybe 200 million years earlier, because we could start thinking about those kinds of questions. And also, that's when the moon was so close to the Earth. So if the Procession dynamo was going, it should have been going gangbusters at that point. And there could have been huge fields generated by that. So if we could get an earlier record, that'd be very valuable.
Okay. Our next question is whether the Earth's magnetic field was ever strong or extensive enough to affect lunar rocks.
Yeah, so dipole fields fall off as 1 over r cubed. So by the time you get to the moon, even a very long time ago, you're still in the nanoteslas range. So this is not a thing.
Yeah, if you put the moon at the Roche limit of the Earth, that is where it would be torn apart by tides, which is obviously the closest you can put it. And you assume that the Earth's field was similar strength then as it is today. It's hard for it to be much more than 10 times that. Then you basically get values around that 0.1 microtesla to 1 micro. The weakest values we would ascribe to a dynamo. You could maybe get to those. So yeah, you can't explain these. Even Sonia's 15498 late dynamo sample by that process.
And someone asked a similar question, sort of in the opposite framework, which was, what effects could a lunar dynamo have had on Earth's magnetosphere?
I'd say the same answer, basically.
Mm-hmm.
There is an idea that, if you don't mind me just going on a tangent slightly, that you could determine the lifetime of Earth's dynamo by looking for gases implanted in the lunar surface from the pre-dynamo epoch on the Earth. I think they're talking about nitrogen and argon. So there's this idea that if you could measure implanted gases that would have been trapped by Earth's magnetosphere, you could actually time the Ordset of Earth's dynamo by looking at the Lunar Regolith gas record, essentially. But it's pretty speculative but interesting idea.
Right. We also had a question on if you could elaborate on the mechanism that's thought to have driven dynamo-inducing precession for 1.5 billion years.
Yeah. It's kind of hard to do this without like a visual aid. But the general, even if you have a visual aid, it's a little complicated. But basically, the idea is that the moon is like, the mantle is like kind of it's not completely spherical. It's a little bit bulging. And so there's like a tidal bulge, and the Earth's gravity is pulling on the tidal bulge, and it's making the mantle like wobble around as it moves. And so the idea is that the mantle of the moon, as it's precessing, as it kind of over time evolves in its orbit around the Earth, the mantle's precession becomes decoupled from the precession of the core. And so they're kind of, it's like they're precessing around different axes. So the idea is if I like slosh, like let's say my soda bottle is the mantle, and I always do this. The Coke bottle is the mantle, and then the liquid, like my Coca-Cola, is the lunar core. If I move my bottle around, and the label's getting in the way, but the idea is that I move the bottle and the core gets sloshed, right? So that's my like very simple way of thinking about it. So that's generally what's happening, is that the differential rotation of the mantle is causing instabilities in the core. And then that's pretty powerful. Like I'm barely jiggling my bottle around and I'm getting a lot of sloshing. So the idea is that you could generate a pretty strong dynamo that way. And like very quickly.
Yeah, fundamentally what you have to do, a dynamo is basically where motion of a conducting fluid in the presence of an arbitrarily weak field leads to currents by Faraday's law. So induction of, basically motion of a conducting fluid leads to magnetic field generation by the process of induction. So what fundamentally you need is you need to get the fluid moving somehow. So we've talked about a bunch of different ways. Convection, that's like your lava lamp, or you could put a blender in there and turn on the blender, and effectively what Sonia just showed you is like not quite a blender, but it's the same kind of mechanical dynamo. You use basically physical motion to move the liquid. You got to get the liquid moving somehow.
What are your thoughts on how lunar paleomagnetism and the record of lunar magnetism can supplement our understanding of long-term solar variability? Ask someone in the class.
Solar variability. Okay, I'll take a, it sounds like I can go in any direction I want with it. Well, one thing people have talked about, and it is an interesting question in the sense that people have talked about whether you could tell the evolution of the sun in time via implantation of the solar wind. We have these, one of the most amazing things we have from the moon are these samples of the ancient regolith. So we have this soil there now, but then we have rocks like what Sonia and I showed you actually. Those are regolith breccias. What are they? They're basically soil that got welded together into a rock by an impact. And we have rocks like that made out of surface materials that go all the way back to more than 3 billion years old, maybe up to almost 4 billion. So we have these truly ancient, basically rock record of the soil. And the soil, lunar soil, is full of gases. It's extremely gas rich. And it's because it's basically exposed to the solar wind over time, and which gets implanted in grains. And so for a long time, from the beginning of the Apollo era, people have recognized that this suite of regolith breccias are an archive of essentially the composition of the sun in time. And so they've tried to infer stellar evolution from that. But a problem with that is if the moon, it's always been assumed that the lunar dynamo wasn't strong enough to, or didn't exist at all. But it turns out if there was a magnetic field, it would have shielded the surface from solar wind, or at least fractionated the solar wind composition potentially. Some species might have gotten to the surface and other ones might not have. For example, uncharged species would have no problem getting to the surface, but charged ones wouldn't. So I think a really interesting kind of future direction to think about in terms of the implications of our work that none of us have really even begun to get into in detail is what is this now that we know when the lunar dynamo existed and what its strength was, what does that mean for these solar wind records? How does it, does it really mean that they are, what time of the sun are we actually recording? Are we actually recording the full composition of the solar wind, or is it some fractionated component?
Good answer, Ben. So I had a couple of additional questions. So You showed a map of the, I think it was a prospector, global map of magnetic properties of anomalies on the moon. And can you comment? It looked like there was a large area in South Pole Aiken Basin that had some linear features. Do you want to comment on theories of the origin of that?
Sonia, why don't you take that?
Yeah, so actually there are three hypotheses for what could have generated the anomalies on the southern lunar far side. So one of them, which was advanced by Lon Hood and Natasha Artemieva, is that whenever there were basin-forming impacts on the near side of the moon, those produced impact plasmas, and those plasmas can basically bend magnetic fields and those plasmas move around the moon and condense magnetic field lines at the antipode of each impact location, which happens to be around the northwestern rim of South Pole Aiken Basin. And so the idea is that these very condensed magnetic field lines produce very strong magnetic fields, and that the shock wave of the impact can also create like heating and shock remnant magnetization at that antipode, and you could have magnetization acquired under that scenario. Ben has a postdoc, Rona Oran, who's doing MHD simulations of how these plasmas actually interact with magnetic fields. And I can let him comment on that particular modeling later, but I'll talk about the other two hypotheses. One is a paper that Ben was also on in 2012 that was written by Mark Wazorek, and that paper says that, given the geometry of South Pole Aiken Basin, it's an elliptical crater, implying that there was an oblique impact. So the idea is during this oblique impact, the core of the impactor, the ejecta produced by the core of that impactor would get deposited downrange, and that impactor core metal-rich material was, deposited at the northwestern rim of South Pole Aiken Basin. And if there was a dynamo around at the time that ejecta cooled, that strongly magnetic ejecta would record magnetization during that cooling, and you'd also see that maybe splotched in other places on the lunar surface as well. So that's the ejecta hypothesis. And then there's a third hypothesis that was come up with by Mike Kurucker and other colleagues. And I think, Jim, you might have been a co-author on this one as well.
Yep.
But there's another hypothesis that there is a dike swarm kind of in that general region near South Pole Aiken Basin. And then there are some magnetic lineations that are inferred after you do the inversions to look at the shape of the magnetic sources. And so it's possible that there are mafic dikes that record magnetic fields. The challenge with that one, which is actually something I'm working on right now, is that none of the Apollo samples that we brought back, the Mare basalts, are strong enough to, they're not iron-rich enough to produce the magnetization intensities that are inferred for these strong crustal magnetic anomalies on the moon. And I'm trying to figure out if there's a way to make rocks more magnetic than what we see using petrology. So basically, those are the three hypotheses. And I think if Ben wants to elaborate more in particular on the MHD work that's being done to address the antipodal plasma focusing hypothesis, I think maybe you want to go on with that.
I'll just say quickly, we didn't emphasize this in this talk, but at the start of this, when we started working on this and basically the end of the Apollo era, they had all these magnetic measurements. But most people, including the people who made them, were not convinced that this was evidence for a dynamo, because there was this alternative hypothesis that we've mentioned a few times, that impacts, which produce plasmas, which are, again, conducting fluids that move, that those plasmas could generate magnetic fields, and that the entire lunar paleo intensity record has nothing to do with the lunar interior at all. It's just a manifestation of superficial processes like impacts. And if that's true, then that calls into question everything we're doing anywhere in the solar system with paleomagnetism. So it's a very important question to address. It's another example of how the moon is kind of like a touchstone for understanding basic planetary processes. We need to understand whether plasmas from impacts can generate the lunar paleomagnetic record or not, if we want to use paleomagnetism anywhere in the solar system to understand planetary evolution. So it's a very important question that goes well beyond the moon. And there was this idea from Lon Hood and others, very thoughtful proposal, that there was this antipodal spatial correlation of magnetic anomalies, which happens also to be coinciding with the northern edge of the South Paleogen Basin. That region is antipodal to many of the other near-side basins, recent young ones like Chrysium, Imbrium. And that maybe those impact anomalies are evidence that there was a plasma cloud that converged at the antipode from those basin-forming impacts, and that basically created or amplified the magnetic field. So it was a thoughtful proposal. No one had really tested it using magnetohydrodynamics, and so that's what Rona Aran has been doing. She actually just showed me the latest results today. We've been working on this for quite a long time now. But basically, to make a long story short, there is a little bit of amplification, but it's nowhere enough to explain the intensity that's required to explain the lunar paleointensity record. So, so I consider that one less likely now, based on our simulations, or I would consider it unlikely. So I think the two leading ideas are the Dike scenario and the possibility that there's some magnetic anomalies associated with iron-rich materials produced by impacts.
So just to follow that up, everybody in this room is interested in being involved in a mission tomorrow or next week or maybe next month. So I'm interested in what you would say might be the types of mission you would send to the South Paleogen Basin to kind of like distinguish between those hypotheses. Could something like Space IL landed in the right place do that job?
Well, just quickly, if the hypothesis that is from iron-rich materials produced by South Paleogen or other impactors, that hypothesis has been invoked because, as Sonia already said, most lunar materials are not sufficiently magnetic to explain these anomalies. So if we brought back samples from South Paleogen and they were anomalously iron-rich, more iron-rich than any other material. So it wouldn't even be necessarily a magnetic measurement, although of course we could measure their remnant magnetization as well. But even just what's their metal content, that would be an extremely important observation. On the other hand, if there's absolutely nothing unusual about the rocks there, then you might suggest that the fields are deep-seated. If something like a South Paleogen Basin lander could bring a little magnetometer on board, they weigh almost nothing, and determine what the fine scale field is. You could start imagine these linear features. What would be for me a convincing evidence that's dikes? Well, imagine you fly over and you map these things at high resolution. They really look like dikes. You really establish that they're linear and they have the sinuous textures or shape that we expect, and there's maybe even some surface correlation with volcanic vents or something like that you couldn't see from orbit. Some high resolution data would be very interesting. Of course, also, I'll shut up then. I'll say one other thing. Imagine there was an impact that's excavated them, and you find Sonia's, ilmenite breakdown samples. So you could even imagine a sample from the subsurface that would allow you to test this. Anyway, sorry, Sonia.
Yeah, well, I was going to add to this, but another way to attack the problem is something that Doug Hemingway and I have been working on is by looking at lunar swirls. And actually, if you look at a map of lunar swirls, there is a large concentration of lunar swirls around the same area, around South Paleogen Basin. And so we published a paper earlier this year that says, based on the geometry of the light to dark transition of lunar swirls, so the idea is that in places where the magnetic field that's emanating from the rocks is horizontal, you protect the surface from solar wind. In places where the field is vertical, you have the solar wind that gets implanted there and causes space weathering and darkening. So basically, the light to dark transition length scale at lunar swirls is indicative of the magnetic field topology and the length scale of the magnetic field. And so based on our analyses, the most likely way to explain short light to dark transitions at lunar swirls, of these albedo anomalies, is to show that the magnetic sources are shallow and narrow. And Ian Garrick Bethel has a kind of an alternative hypothesis, which I think currently might work for Reiner Gamma, which is one particular lunar swirl, but you could also have like a buried impact melt sheet that could have a similar magnetic field topology produced. But in general, you need kind of shallow and narrow sources, and that would be, possibly consistent with ejecta if it's deposited in narrow rays or something like that. So if you have the right morphology, you could get this kind of swirl light-dark transition. But it's also consistent with dikes because dikes are narrow and can be implanted shallowly in the crust. So there's a few ways to look at it, and it's going to take a combination of measurements of the field that are very close to the surface, so we can actually see, variations in how the magnetic field changes on these short length scales, and that might give us some more information about the origin of the anomalies.
That sounds great, and I'd be in touch with you all too about some new ideas we have about the differences between modes of emplacement of lava flows and then the residual dikes as well. So there may be something in there in terms of the strength orientation and the general magnitude of these as well. And we're getting pretty wide dikes, like up to several hundreds of meters. So I'll be in touch. We can maybe talk a little bit more about this as well.
Fine, but it's actually like within the length scale that might be consistent with swirl. That's interesting. Yeah.
I was thinking really that more of the South Pole Aiken examples, et cetera. I understand. So just one other one is the Ben, if you could talk a little bit more about the Space IL, the magnetometer on board, and what you hope, where it's going to go, and what you hope that you might learn from that in the overall scheme of the presentation.
Yes, I was hoping you could tell me. I know surprisingly little about what they're about to do, and I think part of that is because they were competing against the other Google Lunar X Prize missions, so they naturally have been a little bit quiet about, but they, as far as I know, they have not announced their landing site. So I'm actually kind of on pins and needles myself. Maybe
let me ask it another way, because I hadn't realized they hadn't announced it, and I don't plan to do that here. To ask it another way, so if we have this capability, where can we target that to get answers to a lot of the questions? It's a little bit like this. Right?
Yeah, I think like I feel like some of the most transformative things that we could do with in situ exploration, so obviously we'd like to bring samples back. So I didn't really emphasize that in the part I was talking about. But that certainly bring samples back, and ideally oriented ones from bedrock. But if you can't do that, access to slopes, because we think on the moon, bedrock tends to be exposed where you have steep slopes. So that would be in rills, maybe in the walls of impact craters. For example, we think we see this at Camelot crater in Apollo 17. And lava tubes, or these, like where moon divers going. All of those places, by definition, are hard to access with a normal kind of roving platform. So anything that's mobile, that's able to go on steep slopes, I think is like an ideal platform. So that anything that could hover, like a hopper, or could rappel down a stratigraphy. If you could imagine just measuring. So I'm thinking what kind of motivates me this is that, the way the Earth's magnetic field was shown to reverse, which is, when you think about it, a crazy idea, right? That the Earth's field flips. It's like a nut idea. And people didn't believe it for a while. They found, in the early 20th century, they found rocks that were magnetized in the opposite direction of the present day field. And so for a long time, people were convinced that was just something weird about those rocks. They don't know how to record fields right. They get it wrong. And in fact, it is true that there is a small fraction of rocks that become reversely magnetized. But what convinced people that the Earth's field actually reverses, and what initiated the construction of the magnetostratigraphic timescale for the Earth, in large part were measurements by this guy Einarsson, an Iceland geologist in the late 50s, who walked around Iceland, which of course is this big pile of fresh basalt, and he basically stuck his little compass up to the outcrop, and everything that was above a certain stratigraphic level, attracted his magnet, and then when he got down, at some depth, everywhere on some altitude, everywhere on Iceland, his compass needle got pushed away, and he made these, what he called magnetogeologic maps, all with in situ measurements. And then that was just with a compass, too, far worse sensitivity than what we have today with magnetometers. And then people brought samples back from these outcrops and confirmed this stratigraphy. And the reason it was so important is that he showed that everywhere the field was pointing in one direction always had the same age. And then it flipped at the same age everywhere at the same age. So when he got above a certain stratigraphic level, even though all the rocks he was measuring were all basalt, it had nothing, no changes in magnetic properties that could explain that. So I think that's the way we're going to start doing this on other bodies. And the first one we should start it with is obviously the moon. So the nice thing is that these magnetometers are some of the lightest and most robust and most space-hardened technologies available, and they're only getting lighter by the day. So,
and they're inexpensive.
Anytime there's a lander, we should stick one on there. So,
and they're inexpensive too, right?
Yeah, very inexpensive. Yeah.
I'm pushing for you here. So I think one final question here. So on Apollo 16, at least, there was a portable magnetometer. Palmer Dial and others designed this portable magnetometer. Any results come out of that are of any significance in your studies? It was kind of experimental to try to do, but I just don't know whether it fits in with anything.
Sonia, you want to take that?
I think my understanding is that it's a total field measurement, which means it's just the resultant vector component of the magnetic field at each location. And I don't think it was a continuous measurement either. I think it was like they measured it here, and then they drove around and they measured it here. And then, they did it in like pieces, which is kind of less useful than a continuous measurement, because you can imagine that, let's say you land on like a strongly magnetized impact melt rock, like right here, and you just measure one point, and then you go measure next to another rock that's less magnetic. It's interesting, but it's not necessarily the most meaningful in terms of interpreting what geology is responsible for producing the field that you're measuring, as well as what the direction of the field is. Then you can learn something about the length scale of changes. But it was interesting, but we can't do much with that. And I think that's what I'm aware of, at least.
Yeah, and I was just saying it suffers from the problem associated with it being regolith instead of bedrock, which we really like.
Right. So we really want to thank Sonia and Ben very much. This is very informative, excellent discussion afterwards as well. And I want to just summarize here by summarizing our upcoming events. So in 2 weeks, Lindy Elkins-Tanton will talk to us essentially about the models for the thermal evolution of the moon. The readings for that are already on the website. And then don't forget, December 19th, future exploration of the moon. We're going to finish up with the road ahead, and Apollo 17 astronaut Harrison Jack Schmidt will be talking there. I talked to Jack last week at the Geological Society of America meeting, and he's all really excited and interested to do the class and take us into the future. So again, we will not have a class on Thanksgiving. So the next class with Lindy will be in 2 weeks, and then we will also not have a class for the AGU meeting, as most of us will be there. So in between that, on December 5th, the Lunar Polar Deposits in Surface Water by Dana Hurley and Ralph Millikan. And so I encourage you to check out the website, do the readings, and we'll be back to you soon. And on behalf of David Kring at the LPI and myself, again, thank you very much, gang. And I'll be back in touch with a couple of other points to follow up, okay? Thank you. Oh, Ben, who is the guy in the background there? Everybody wants to know.
That's me.
I knew that. I recognize the green. Okay.
Thanks a lot. This is a lot of fun.
Okay, great. Thank you, Sonia. Thank you, Ben. We'll talk to you soon.
Okay, bye.
Bye.